Right now, as you watch this video, there's a spacecraft that could theoretically reach Mars in just 39 days. The technology exists, the math checks out, so why aren't we using it? The answer will change everything you thought you knew about space travel, and by the end of this video, you'll understand why getting to Mars isn't about building faster rockets, it's about surviving the journey itself. Here's what most people get wrong. They imagine a trip to Mars like a road trip. You point your car toward your destination, press the gas pedal, and drive there. Simple, right? But space doesn't work that way, at all. In fact, if you tried to fly to Mars the way you drive to another city, you'd end up dead in the darkness of space, billions of kilometers from where you intended to go. And that's not an exaggeration. Let's start with something that sounds insane, but is absolutely true. When NASA launches a mission to Mars, they don't aim at Mars. They aim at empty space, a point in the void where Mars isn't even located yet. They're essentially throwing a dart at where a moving target will be 7 months from now. And if they're off by even a tiny fraction, the entire mission fails. But why 7 months? Why not 7 weeks or 7 days? The problem isn't the rocket. Modern rockets are incredibly powerful. The Falcon Heavy can generate over 5 million pounds of thrust. That's enough to lift a 737 airplane straight up into the sky. We have the power. What we don't have is a way to use that power continuously for months on end. And that limitation creates a cascade of problems that most people never think about. See, when you launch from Earth, you're not starting from zero speed. Earth is already moving around the sun at 107,000 kilometers per hour. You're on a cosmic carousel whether you realize it or not. And Mars? It's on its own carousel, moving at 86,000 kilometers per hour. Both planets are racing around the sun at different speeds on different tracks, and you need to jump from one moving carousel to another. Except these carousels are separated by hundreds of millions of kilometers of absolute nothingness.
Imagine you're on a highway doing 100 kilometers per hour, and you want to merge onto another highway that's also doing 100 kilometers per hour, but in a completely different direction. You can't just turn your steering wheel and hope for the best. You need to gradually adjust your speed and direction. But in space, there's no friction to help you slow down, no air to push against. Once you're moving, you keep moving at exactly that speed in exactly that direction forever, unless you fire your engines. And here's the brutal truth about rocket fuel. It's heavy. Incredibly heavy. For every kilogram of spacecraft, you need multiple kilograms of fuel just to get it moving. The SpaceX Starship, designed for Mars missions, will carry about 1,200 tons of propellant just to get off Earth. That's the weight of roughly 200 elephants. All of that fuel burns in minutes, and once it's gone, it's gone. You're coasting through space with whatever velocity you manage to reach. So why can't we just pack more fuel and go faster? Because of something called the tyranny of the rocket equation. It's one of the most frustrating laws of physics for space engineers. Here's how it works. If you want to go twice as fast, you don't need twice as much fuel. You need exponentially more. We're talking 10 times, 20 times, maybe even 50 times more fuel depending on how much faster you want to go. And all that extra fuel makes your rocket heavier, which means you need even more fuel to lift that fuel, which makes it heavier still. It's a mathematical nightmare. Engineers call it a runaway problem. Every solution creates a bigger problem. That 39-day trip I mentioned at the beginning, theoretically possible with nuclear propulsion, but the amount of fuel and the technology required would make the spacecraft so massive and complex that we literally don't have the infrastructure to build it yet. We'd need to assemble it in orbit, fuel it in space, and solve a dozen engineering challenges we haven't figured out. But let's say we somehow solved the fuel problem. Let's say we built a rocket that could accelerate continuously and reach Mars in 39 days instead of 7 months. Would we use it? Actually, no. And the reason why reveals something most people never consider about space travel.
Speed in space isn't just about engineering. It's about biology.
Your body wasn't designed for high-speed interplanetary travel, and when you start cutting down travel time dramatically, you run into problems that have nothing to do with rockets and everything to do with the fragile meat sack we call the human body. First problem: acceleration. On Earth, you feel 1 g of gravity pulling you down constantly. It's comfortable because you evolved in it, but when you accelerate in space, you create artificial gravity through thrust. The faster you want to go, the more you need to accelerate. And sustained acceleration above 1 g for weeks becomes torture. Your blood pools in the wrong places, your organs compress, your bones stress. Astronauts can handle brief periods of high g-forces during launch, but living in them for days or weeks, that's a medical nightmare we haven't solved. Second problem: radiation. Earth's magnetic field protects you from cosmic radiation and solar particles every single second of your life. Once you leave that protection, you're exposed to radiation levels that are genuinely dangerous. The longer you're in deep space, the more radiation you accumulate. Now here's the twist. Going faster to Mars sounds like it would reduce your exposure, right? Less time in space means less radiation. But if you're accelerating harder to get there faster, you might need to take a trajectory that exposes you to more intense radiation fields. You're trading one risk for another. Third problem, and this is the one nobody talks about: stopping. Let's say you build a super fast rocket that can get you to Mars in 30 days. Amazing, right? Wrong, because now you're approaching Mars at absolutely terrifying speeds. You need to slow down before you get there, or you'll just shoot right past it into the outer solar system. And slowing down requires just as much fuel as speeding up. That means you need even more fuel, which makes your spacecraft even heavier, which means you need more fuel to move that weight. See the pattern? Every solution branches into multiple new problems. This is why NASA, SpaceX, and every other space agency still uses that slow, patient 7-month trajectory we talked about earlier. It's not because they're not ambitious, it's because it's the only method that balances all these competing factors: fuel efficiency, human safety, and mission success. But here's where things get exciting. We're not stuck with 7-month trips forever. New technologies are in development right now that could genuinely change the game. And I'm not talking about science fiction. I'm talking about projects that have funding, testing, and realistic timelines. Nuclear thermal propulsion is probably the closest to reality. Instead of burning chemical fuel, you use a nuclear reactor to superheat hydrogen and blast it out at much higher speeds. This could cut travel time to around 3 to 4 months, without requiring impossibly large amounts of fuel. NASA is actively testing these engines right now, with plans for Mars missions in the 2030s. Then there's nuclear electric propulsion, which is even more efficient. These engines produce a tiny amount of thrust, but can run continuously for months. Imagine instead of one big burn followed by months of coasting, your spacecraft is gently accelerating the entire journey. It's like the difference between sprinting for 30 seconds and then walking for an hour versus jogging the entire time. NASA's been testing these systems too, and they could reduce Mars travel to around 2 months. And if you really want to get wild, there's something called a Vasimer engine, a plasma rocket that theoretically could get humans to Mars in just 39 days. That's the number I teased at the beginning. The technology has been tested in labs and it works, but it requires enormous amounts of electrical power, which means either a huge solar array or a compact nuclear reactor. We're probably 20 to 30 years away from seeing this on an actual Mars mission, but the physics checks out. Here's what's important to understand. The reason we can't just fly to Mars quickly isn't about lack of ambition or funding, though those help. It's about the fundamental physics of moving massive objects through the vacuum of space while keeping humans alive. Every breakthrough we make in propulsion technology has to be matched by breakthroughs in life support, radiation shielding, and spacecraft design. So when someone asks why we can't just build a faster rocket to Mars, the real answer is we can. But building the rocket is the easy part. The hard part is making sure humans survive the journey, can actually stop when they get there, and have enough fuel left over to come home. Space travel isn't about doing things fast, it's about doing things smart.
The current 7-month journey to Mars isn't a limitation, it's a solution. It's humanity's way of threading the needle between what's physically possible and what's practically survivable. And as our technology advances, that needle will thread differently. The trips will get shorter, safer, and more routine. But we'll never escape the fundamental realities of orbital mechanics, the rocket equation, and human biology. We just learn to work with them better. If this made you see space travel in a completely different way, hit that subscribe button. We're diving deep into the engineering and physics that makes the impossible possible. Next video, we're covering why landing on Mars is actually harder than getting there in the first place. Trust me, you don't want to miss that one. I'll see you in the next video.